Long before modern science, that there were these ancient geniuses that were building machines, theories, and technology so advanced they could have passed for alien artifacts. These 15 inventions weren't just early, they were centuries, sometimes millennia ahead of their time. So let's start with number 15, the hero of Alexandria's steam engine, Egypt in the 1st century CE. Nearly 2,000 years before the Industrial Revolution changed the face of the world with steam-powered machines, a Greek-Egyptian inventor named Hero of Alexandria built a device that could have sparked it centuries earlier if the world had been ready. His creation, called the Eulapile, was a spherical steam engine that rotated on its axis using nothing but pressurized steam and mechanical principles. While simple in structure, it was so far ahead of its time that most historians overlooked its true potential for centuries. Hero lived during the 1st century CE in Roman Egypt. That was a crossroads of culture, science, and engineering. He drew upon earlier Greek knowledge and Egyptian mechanical tradition, and he compiled his inventions in a series of books, most notably Pneumatica. Within its pages, he described dozens of machines powered by air, water, heat, and pressure. But none stood out more than the Eulapile, a hollow metal sphere mounted on a pair of pivoting tubes, with 2 bent nozzles protruding from its sides. When water inside the sphere was heated, steam would rush out of the nozzles, causing the sphere to spin rapidly like a primitive jet engine. It was quite literally a rotary steam engine, predating James Watt's famous design by more than 1,600 years. And he didn't stop at just building a single spinning toy. He proposed a range of steam-powered devices, including automatic doors, coin-operated dispensers, and mechanical puppets, all controlled by heat and pressure. His machines were not only theoretical, many were actually built and may have been used to impress temple-goers in Alexandria and other cities with miraculous technology that was disguised as divine intervention. So why didn't this spark a technological revolution? Well, there's several theories. First, the Eulapile was likely a curiosity, not a practical engine. Hero's world was driven by slave labor and animal power, and the idea of using machines for work rather than spectacle simply hadn't taken root in the cultural mindset. Additionally, metallurgy and material science in the ancient world weren't quite yet advanced enough to build pressure vessels or turbines on an industrial scale. Still, the fact remains, Hero built a working steam engine in a society that didn't need one. He described pressure differentials, valves, feedback systems, and automated motion long before those concepts were formalized in engineering. In effect, he cracked the code, then he left it untouched for nearly 2 millennia. Only in the 18th century, with the rise of industrial manufacturing and economic systems that required mechanization, did humanity rediscover what Hero had already demonstrated, that heat could drive machines, and machines could change everything. Today, the Eulapile is studied in engineering courses and it's replicated in museums and classrooms, a whirring bronze globe that symbolizes how far imagination can go when it isn't yet shackled to utility. Hero wasn't just ahead of his time, he was standing in the future, just trying to hand us the blueprints. Number 14, the Baghdad Battery, Iraq, circa 200 BCE. Tucked away in the basement of the National Museum of Iraq, hidden behind dusty display cases and decades of speculation, sits one of the strangest archaeological discoveries ever made, a clay jar with a copper cylinder inside it and an iron rod sticking out of the top. Now, at first glance, it looks like an ordinary storage vessel, but to some scientists, it may be something far more provocative, an ancient galvanic cell, a battery. Discovered in the 1930s near modern-day Baghdad, this object, now dubbed the Baghdad Battery, dates to the Parthian and Sassanid period, somewhere between 200 BCE and 250 CE. Its construction is deceptively simple. It's a 5-inch terracotta pot, inside of which sits a rolled copper sheet sealed with asphalt. Down the middle runs an iron rod, also isolated from the copper by the bitumen stopper. When replicas of this device were filled with weak acids like vinegar or lemon juice, they produced a small but measurable electrical charge, typically around 0.5 to 1 volt. Not much by modern standards, but for an object over 1,800 years old, that is nothing short of revolutionary. If it really was a battery, the implications are pretty staggering. It would mean that ancient civilizations in Mesopotamia understood the basic principles of electrochemistry and maybe even used them for practical or ritualistic purposes. So, what was it used for? Well, no written records have been found to confirm the battery's function. However, some researchers suggest it could have been used in electroplating, a process by which a thin layer of metal is deposited onto another material. Now, that theory gained traction when unusual gilding and plating techniques were found on artifacts in that region, some of which could not easily be explained by traditional methods. Others believe the battery may have been used in medicine, maybe to apply mild shocks for therapeutic purposes, and that's a practice seen centuries later in Greco-Roman medical texts. Still others suggest a religious function, an object that could produce a magical tingle or a spark in temple rituals, impressing believers with what appeared to be divine energy. Critics argue that the Baghdad battery might simply be a storage vessel or a scroll holder, and that the electrical charge produced by replicas is coincidental. But even skeptics agree that the construction is anomalous. No similar items from that era match its composition or even shape. This raises a tantalizing possibility. Maybe the Baghdad battery was a singular invention, discovered by accident or crafted by a single innovator whose knowledge wasn't passed down, a lone moment of brilliance in the dark. For decades, the battery remained a fringe fascination until the advent of modern science began to vindicate the plausibility of these ancient energy devices. It even inspired episodes of Mythbusters, which tested working replicas, and it confirmed that the jars could generate enough voltage to electroplate a small silver object. Regardless of whatever theory holds true, the artifact does stand as an example that innovation is not linear. Ideas don't always progress. They appear, they can vanish, and sometimes they resurface centuries later. Whether or not the Baghdad battery lit up lamps or plated jewelry, one thing's clear. It sparked one of the longest-running scientific debates in archaeology, and it may yet hold secrets that we still don't know how to measure. Number 13. The South-Pointing Chariot, Ancient China, the 3rd century CE. Long before the invention of the magnetic compass, before GPS, and even before Europe began seriously exploring the open oceans, Chinese engineers built a land vehicle that could do something seemingly impossible: always point south, no matter which way it was turned. This marvel of mechanical ingenuity was known as the South-Pointing Chariot. It wasn't powered by electricity or even magnetism. Instead, it used pure mechanical gearing, an intricate differential system to maintain directional orientation. Now, imagine a cart. No matter how the wheels are turned, a figurine mounted on the top always continued pointing in the same fixed direction. To modern engineers, that may sound like a challenge from an MIT robotics course. To Chinese inventors of the 3rd century CE, it was a functional physical reality. The first record of the South-Pointing Chariot dates back to the Three Kingdoms period, particularly to the state of Wei under the leadership of Zhuge Liang, a military strategist and polymath. However, some accounts suggest that the concept may have originated even earlier, during the Zhou dynasty around 1000 BCE, and it was reinvented multiple times throughout Chinese history. But how did it work? At the heart of the chariot was a differential gear. Now, that's a mechanism that would later become essential in automobile engineering. This system allows for the rotation of the wheels at different speeds while maintaining a fixed orientation for the figurine on top. As the chariot turned, the gears compensated for the movement, keeping the pointer consistently aligned in the southern direction. Now, this wasn't some theoretical machine. There are historical records of emperors using these chariots in ceremonial processions, and reconstructions during the Song dynasty suggest that the device was real. The chariot's implications, though, went far beyond engineering. It demonstrated the Chinese mastery of mechanical logic, centuries ahead of its time. While the West was still experimenting with crude water wheels, Chinese inventors were exploring directional control through gearing, a concept that wouldn't become widely adopted in the West until the 19th century. Well, regardless of its purpose, the chariot does stand as a mind-blowing example of non-electric navigation in the ancient world. It relied entirely on human movement and precision gear work. No magnets, no compasses, and no electronics. It is like watching an analog computation in motion. Modern historians have recreated the chariot based on surviving descriptions, confirming that the principle does work, though only with incredibly precise machining and flawless calibration. That such a feat was achieved in antiquity is an example not only to China's technical capability, but to a broader truth. Innovation doesn't always follow the path we expect. Sometimes it loops back thousands of years before history can catch up. Number 12. Damascus steel, Middle East and South Asia, 500 to 900 CE. To the untrained eye, it looks like any other blade, but when you tilt it to the light, you see these flowing patterns like ripples on dark water. These blades, forged in ancient India and later refined in the Middle East, were stronger, sharper, and more flexible than anything Europe would produce for another 1,000 years. They were known as Damascus steel, and for centuries, the secret was lost. These legendary weapons could cut through lesser swords, slice silk in midair, and retain their edge through brutal combat. Crusaders returning from the Middle East brought back stories of these miraculous blades, crafted by Islamic smiths using mysterious ingots called woots from southern India. But no matter how hard Western metallurgists tried, they couldn't replicate it. So what exactly made Damascus steel so special? Well, it wasn't just metallurgy, it was nanotechnology before that word even existed. The ancient smiths who created Damascus blades used a forging process that manipulated carbon and carbide formations at the molecular level. The exact method, folding, hammering, tempering, all created a material with a unique combination of hardness and ductility. That is, it was strong without being brittle, capable of maintaining a razor edge while resisting breaking. The exact forging method, however, was never fully written down. It was only passed down orally, master to apprentice, and often it was in secret. By the 18th century, this art had vanished. The depletion of high-carbon Indian ore, combined with colonial disruption and industrial iron production, meant that true Damascus steel was lost to time. It wasn't until the modern era, using electron microscopes, that researchers finally cracked the code. Scientists discovered that real Damascus steel contains these things called cementite nanowires. These are carbon-based structures that help explain the material's strength and flexibility. These microscopic patterns, only now visible, had been manipulated by the ancient artisans with no concept of atomic structure, yet somehow they did it anyway. Modern steel can now exceed Damascus steel's capabilities through precision alloying and control over carbon content, but the romance of Damascus remains. Today, knife and sword collectors treasure original pieces not just for their edge, but for what they represent, the pinnacle of lost ancient technology. More than a weapon, Damascus steel is a reminder that craftsmanship once achieved feats that science is now only beginning to explain. Number 11. The Byzantine fire siphon, 7th century CE. In the shadow of the crumbling Roman Empire, a new kind of warfare emerged, one that defied the logic of medieval weaponry, and it terrified enemies with a seemingly supernatural power. The Byzantines called it liquid fire, or Greek fire, and it was launched not from catapults or arrows, but from handheld pressure devices mounted on ships. These were the world's first flamethrowers, and the invention behind them, the Byzantine fire siphon, was so advanced that it wouldn't be replicated for another 1,000 years. Greek fire was a closely guarded military secret of the Byzantine Navy, deployed primarily during naval battles against Arab fleets during the 7th to the 12th centuries. But what made it terrifying wasn't just the flames. It was the substance that could burn on water. Dousing it only made it spread, and sailors had no defense against it once ignited. The mechanism that deployed it, however, was just as revolutionary as the substance itself. According to 10th century Byzantine military manuals and Arab eyewitness accounts, ships were equipped with bronze siphons, devices that used pressurized tanks and valved piping systems to shoot streams of Greek fire like jets of liquid napalm. These weren't mere hoses, they were complex multi-component machines that combined liquid propulsion, combustion ignition, and controlled targeting, centuries before the first flamethrowers of World War I. Though the formula for Greek fire has never been recovered, historians suspect it involved naphtha, pine resin, quicklime, and possibly sulfur or saltpeter, materials that were volatile and highly reactive. But the real mystery lies in the mechanical deployment, the siphon system. It required pressurized containment of a volatile liquid, a means of controlling flow, a reliable ignition system, possibly using a pilot flame or a flint spark, heat shielding to protect the user, and consistent pressure delivery, despite ship movement and vibration. These are non-trivial engineering feats, especially in the 7th century. Modern reconstructions suggest that the Byzantines used bellows, piston pumps, or even bronze tanks heated to increase pressure. But its impact was devastating. Greek fire gave the Byzantines a century-long strategic edge at sea, repelling Arab invasions and protecting Constantinople in critical battles. The secrecy surrounding this device was so intense that its production was compartmentalized, only with a few families allowed to even manufacture the components. By the 13th century, after repeated sieges and the decline of Byzantine power, the knowledge was lost. The concept wouldn't re-emerge until Leonardo da Vinci's sketches, and not fully be weaponized again until the 20th century. Today, the fire siphon is regarded not only as a tactical marvel, but as a mechanical invention that defied its era. A pressurized, fuel-based projection system way ahead of anything seen in medieval Europe or Asia. It is a haunting reminder that sometimes military innovation doesn't just outpace the enemy, it outruns time itself. Number 10. Ancient Roman concrete, about 100 BCE to 300 CE. When most people think of ancient Roman engineering, they picture aqueducts, amphitheaters, or majestic domes. What they rarely think about is the one invention that made that all possible, and that's still outperforming modern equivalents 2,000 years later: Roman concrete. Known to the Romans as opus cementitium, this construction material was lighter, stronger, more resilient, and way more durable than many modern concretes. Unlike today's Portland cement, which can degrade just after about 50 to 100 years, Roman concrete structures like the Pantheon, the Colosseum, and countless other aqueducts and seawalls are still standing, often in structurally sound condition. So what was the Roman secret? Well, the core innovation lay in their use of volcanic ash, particularly from Pozzuoli near Naples. When mixed with lime and seawater, the resulting binder produced a chemical reaction that continued to strengthen the concrete over time. Instead of weakening like modern cement exposed to salt water, Roman concrete used it as a reinforcing agent. Modern studies by geologists and material scientists have revealed that Roman concrete's longevity comes from the formation of aluminous tobermorite and phillipsite crystals inside the concrete matrix. Those are minerals that grow over time and seal microcracks, essentially self-healing the material. This discovery stunned researchers. It meant that Roman concrete wasn't just durable, it was chemically alive, improving with age. The Romans understood this, at least observationally. In his architectural treatise De Architectura, Vitruvius emphasized the importance of using volcanic ash in harbor construction, noting that it hardens underwater. He didn't know the geochemistry, but he knew the effect, and so did Roman builders who used that knowledge to create things like domes with no internal reinforcements, harbor piers that resisted wave erosion for millennia, and vaulted ceilings 150 feet across still intact today. But perhaps the most stunning example is the Pantheon in Rome, completed around 126 CE. Its dome is made of Roman concrete, and it's still the largest unreinforced concrete dome in the world. It survived earthquakes, weather, wars, and pollution, not because it's thick or heavy, but because the Romans graded the concrete by density, using lighter materials like pumice at the top and heavier stone near the base. So what happened? Why did we forget this recipe? Well, as the Roman Empire fell, trade routes to get this ash were disrupted. Architectural knowledge became fragmented, and by the Middle Ages, concrete construction had declined. It wasn't until the 18th and 19th centuries that concrete re-emerged. But by then, the formula had changed. Those self-healing properties were lost, and with them, 1,000 years of resilience. The story of Roman concrete is not just about longevity. It is about how deeply empirical knowledge, driven by observation and experience, can outperform even the most mathematically derived modern solutions. It reminds us that progress is not always facing forward. Sometimes it means looking backward with eyes that are newly opened. Number 9. The Sunstone, in the Viking Age, 900 to 1200 CE. Imagine, you're sailing across a cloud-covered ocean with no compass, no GPS, and the sun's hidden behind a blanket of gray. For ancient mariners, this would have meant certain disorientation, but not the Vikings. According to legend and increasingly archaeological and optical evidence, Norse sailors may have used a mysterious navigational tool known as the sunstone, a crystalline object that allowed them to locate the sun's position even when it wasn't visible. For centuries, the sunstone was considered a myth, mentioned in Icelandic sagas, and in one passage, a Viking uses a sunstone to determine the position of the sun during snow and overcast skies. For a long time, historians debated whether this was poetic metaphor or actual technology, but in the last few decades, that skepticism has evaporated. Scientists now believe that the sunstone was very real, and it may have been one of the most sophisticated optical instruments of the early medieval period. So what was it? Well, researchers now think that the Viking sunstone was likely a piece of Iceland spar. That's a type of calcite crystal with a unique property known as birefringence. When light passes through it, the crystal splits the beam into two separate rays. This causes objects seen through the crystal to appear doubled, but it also allows observers to determine the direction of polarized sunlight, even when the sun is obscured by clouds or fog. Its polarized light patterns remain detectable in the sky. By rotating the crystal and observing how the double image aligns or can dim, a skilled navigator could pinpoint the sun's exact location within a few degrees, even in conditions where celestial navigation would be impossible. And by the way, this is no longer all speculative. In 2011, a calcite crystal was discovered on an Elizabethan warship wrecked in 1592, the HMS Alderney, suggesting that this technology may have spread beyond the Viking use. Laboratory tests have since confirmed that Iceland spar can indeed be used for polarized light navigation, and that it works remarkably well under overcast skies or near twilight. This technology was centuries ahead of its time. The scientific understanding of light polarization didn't emerge until the 19th century. Yet Norse sailors, without modern optics or even theory, had discovered and applied it in a practical, operational context, likely all passed down through oral tradition and apprenticeship. The implications of this are massive. It helps explain how Vikings successfully voyaged across the North Atlantic to places like Iceland, Greenland, and even North America, what they called Vinland, long before compasses were even introduced to Europe. The sunstone would have been a game changer for open ocean navigation, especially in polar and high latitude regions where the sun's position is critical but often obscured. What's most remarkable is not just the crystal, but the knowledge behind it. Someone had to observe how light behaved through the stone, experiment with it, then teach it to other users. That's science, observation, and engineering centuries before modern physics could explain why it worked. The sunstone, it's not just an artifact of Viking exploration, it is a symbol of how ancient humans could perceive and harness forces that even today remain largely invisible. Number 8. The Chinese seismograph, the Han Dynasty in 132 CE. In the year 132 CE, a massive earthquake shook the Chinese countryside. But before the shaking was even felt in the capital, an ornate bronze vessel in the imperial court had already recorded its direction. This device, invented by polymath Zhang Heng, was the first known seismograph, an astonishing scientific achievement over 1,700 years before the modern seismometer. The device resembled a large bronze urn or cauldron roughly 6 feet in diameter, adorned with 8 dragon heads mounted around its rim, each representing a compass direction. Beneath each dragon was a bronze toad. Its mouth was open as if waiting to catch something. Inside the urn, a delicately balanced pendulum or inverted column was suspended. When an earthquake happened, no matter how far away, a seismic wave would subtly disturb the internal pendulum, causing it to tip in the direction of the wave's origin. This in turn triggered a mechanical linkage that opened the mouth of one specific dragon head, dropping a ball into the corresponding toad's mouth below. Officials would then check which toad had caught the ball, revealing the direction from which the tremor came. Yeah, that's right. Zhang Heng created a directional earthquake detector over 1,000 years before Europe even understood that earthquakes radiated from a central epicenter. Even more astonishing, historical records suggest that the device actually worked. In one famous account, the seismograph dropped a ball even though no quake had been felt locally. Days later, messengers arrived reporting a major quake hundreds of kilometers to the west, exactly the direction the device had indicated. Modern engineers have tried to recreate this seismograph using his handwritten descriptions and Han-era metallurgy, and reconstructions in China and Japan have shown that while not sensitive enough to detect minor tremors, this device can indeed respond to ground motion, especially large, long-period waves from distant quakes. Though the original device has not survived, the idea has echoed across the centuries, and in many ways, it still defines the spirit of ancient innovation. It's brilliant, imaginative, and it was profoundly ahead of its time. Moving on to number 7, the Al-Jazari automata, the Islamic Golden Age. Long before programmable robots and artificial intelligence, long before gears powered watches or pistons drove engines, one man created a universe of machines so intricate and imaginative that they seemed to belong to a future yet to come. His name was Ismail Al-Jazari, a 12th century polymath from what is now southeastern Turkey, and his crowning achievement was a monumental book titled The Book of Knowledge of Ingenious Mechanical Devices. Within its pages lay a world of marvels: water-powered clocks, self-operating musical automatons, programmable machines, and even robotic servants. Compiled in 1206 CE at the height of the Islamic Golden Age, this book wasn't merely theoretical. It did include detailed illustrations, component breakdowns, and assembly instructions for over 50 mechanical inventions, many of which were built and operated in real places under the Artukid dynasty. Al-Jazari's machines were powered by water pressure, weights, gears, and hydraulic regulators, and some even featured rudimentary forms of programmable logic. One of his most famous inventions was the elephant clock. That was a water-powered timepiece that combined Greek, Indian, Persian, Egyptian, and Islamic cultural elements. It used a system of water-filled buckets, pulleys, and levers to drive mechanical figures, snakes, birds, and a mahout atop the elephant, all of which moved at set intervals to mark the time. Beyond being an engineering feat, it was a symbol of unity through knowledge, showing how innovation can transcend borders and even belief systems. But the elephant clock, that was just the beginning. Al-Jazari also created a robotic musician that was a boat-mounted 4-piece band powered by water flow and rotating drums, programmed with pegs and cams, and arguably the world's first programmable mechanical band. He invented a hand-washing automaton. This was a humanoid figure holding a pitcher, and when the user lifted the basin, the figure poured water, and when finished, the figure offered a towel. Then there was the self-refilling fountain. Using siphons and valves, the system could maintain constant water levels automatically, adjusting to user activity without any manual input. And an automated lamp, powered by rising water and counterweights, which could adjust light intensity over time. Some historians believe Al-Jazari's work represents the origins of robotics. Unlike earlier automata built purely for spectacle, his machines were designed for utility and entertainment, each calibrated with incredible care. And though most of his original devices are lost, modern engineers have recreated many of them based on his diagrams, and they functioned as described. In a time when Europe was just emerging from the early Middle Ages, and when even clocks were rare, Al-Jazari imagined interactive machines, programmable logic, and humanoid helpers. He didn't just anticipate the future. In many ways, he kind of built a working model of it, with nothing but flowing water, gears, and an almost superhuman grasp of mechanical systems. Number 6. The Banu Musa's self-operating fountain in Baghdad. In the intellectual city of Baghdad during the Abbasid Caliphate, knowledge was currency, and invention a form of both art and power. Among the most remarkable contributors to this golden age of science and engineering were the Banu Musa brothers, Muhammad, Ahmad, and Al-Hassan. These three polymaths are best remembered for their masterwork, the Book of Ingenious Devices, a 9th century encyclopedia of mechanical wonders that included some of the first recorded programmable machines. One of the most captivating inventions was the self-operating fountain. That was a machine that could alternate water flow in different directions, simulate multiple pressure outputs, and do so without any human intervention. It was one of the first documented devices to implement switching valves, timing regulators, and fluid-based actuation, all controlled by air pressure and water pressure. Their self-operating machines were made for more than just entertainment. They were technological showcases installed in palaces, gardens, and religious centers, and they demonstrated the harmony between natural forces and human ingenuity. Some were purely functional, early siphon-based tools for irrigation or water management, while others pushed the limits, including self-opening doors powered by pressure gradients, mechanical flutes where water flow generated different tones, and motion-triggered fountains which reacted to environmental changes. What's more interesting is their inventions were scalable. The principles used in the fountain could be applied to irrigation, ventilation systems, bathhouses, and public fountains. And yet their genius faded with time. As the Abbasid Caliphate declined and libraries were destroyed or forgotten, many of the Banu Musa's contributions were lost or obscured. It was only through surviving Arabic manuscripts translated to Latin centuries later that Europe gained a glimpse into this era of innovation. The self-operating fountain wasn't just a technological oddity, it was proof that complex systems could be automated, observed, and controlled using feedback and fluid mechanics. In the 9th century, that idea was magic. In the 21st, it's still genius. Number 5. The Lycurgus Cup, the Roman Empire, circa the 4th century CE. To most people, it looks like a beautiful Roman chalice, carved from glass and set in an intricate cage of bronze filigree, depicting King Lycurgus entangled in vines. But when the light shines through it, the entire cup transforms. Its colors change from opaque green to glowing red. And this is not magic. It's not a trick of paint or pigment. It is nanotechnology, mastered by Roman artisans 1,600 years before the modern microscope. The Lycurgus cup is now housed in the British Museum, and it's one of the few surviving examples of dichroic glass from antiquity. It owes that color-shifting property to gold and silver nanoparticles suspended in the glass matrix. These tiny metal particles scatter and absorb light in such a way that the glass appears as one color reflected light, green, and in another transmitted light, red. It is the same principle used in today's plasma sensors and optical filters, only here it's embedded in a ceremonial cup from the late Roman Empire. Dichroic glass wasn't widespread, and the Lycurgus cup may have been one of a kind. That's part of what makes it so remarkable. Whoever created it had mastered a technique that wouldn't be formally understood until the 20th century, when electron microscopes revealed the existence of particles far smaller than the wavelength of visible light. But these implications go far beyond artistry. This means that Roman glassmakers, while aiming for a visual effect, had accidentally created the foundation for a branch of materials science that now underpins everything from biosensors to quantum computing. Why this technology wasn't more widely used does remain unclear. Some scholars believe dichroic glass was too expensive, requiring rare metals and high failure rates. Others argue that it may have been reserved for sacred or royal use, hidden away in ceremonial contexts. Still though, its very existence challenges our assumptions about ancient craftsmanship. This isn't just a pretty object, it is a functional nanomaterial that was created by trial and error, and genius in an age without chemistry, labs, particle physics, or optical theory. When you look at the Lycurgus cup, you're not just seeing a piece of Roman history, you are staring directly at a 4th century experiment in nanophotonics, still glowing with secrets that the world is only beginning to understand. Number 4. The Sacsayhuam&aacute stone walls in the Inca Empire, circa 1100 to 1500 CE. Above the city of Cusco in Peru lies the megalithic stone walls of Sacsayhuam&aacute, a vast terraced fortress constructed by the Inca civilization. To a modern visitor, the site looks almost impossible. These massive stone blocks, some weighing over 100 tons, are fitted together with such precision that you can't slip a razor blade between them. There's no mortar, no gaps, just stone against stone, perfectly interlocked, forming zigzagging walls that have withstood centuries of earthquakes. How did the Inca achieve this? Well, to this day, no one really knows for sure. The stones are not uniform. They have irregular polygonal shapes, often with 10, 12, or even more sides. Yet each fits into its neighbor like a perfect puzzle. The engineering here is so advanced that the Spanish, upon seeing it, believed it must have been built by giants or gods. Yet no cranes, no iron tools, and no wheels were used here. The Inca never developed a wheel for transport, and no written plans survive. So how did they cut, transport, and place these things? Well, the quarry for many of these stones lies several kilometers away, and that required transport across uneven terrain and uphill elevation. Some theories suggest the use of log rollers, ropes, and massive human labor forces, though even with modern equipment, moving 100-ton blocks without breaking them is pretty difficult. As for the cutting, well, the Inca lacked steel tools, yet these stones, many of which are andesite and diorite, are both extremely hard and they're shaped with uncanny precision. One theory does suggest the use of bronze tools and abrasives, perhaps combined with controlled heating and water fracturing to weaken the stone, but no definitive method has ever been proven. And then there's the matter of design. The entire thing isn't just functional, it is symbolic. From above, the zigzagging walls resemble the teeth of a jaguar, a sacred animal in Incan cosmology. But what makes Sacsayhuam so far ahead of its time isn't just the scale or strength of the architecture, it is the integration of aesthetics, function, and resilience, all without formal mathematics, written blueprints, or modern tools. What we do know is this: the people who built it understood vibration, balance, leverage, and compression at a level that we didn't expect from a pre-literate society, and they translated that understanding into a fortress that 500 years later continues to amaze and raise eyebrows. In a world where ancient monuments are often dismissed as primitive, the walls of Sacsayhuam remain silent but defiant proof that sophistication does not require steel, scripts, or satellites. Sometimes it's just carved directly into the stone. Number 3. The Sanxingdui masks and metallurgy, ancient China, circa 1200 BCE. In the Sichuan basin of southwestern China, archaeologists have unearthed artifacts so alien and so advanced, and so utterly unlike anything seen in traditional Chinese history, that some scholars initially thought they were forgeries. Towering bronze masks with protruding eyes, massive ritual trees of metal, intricate gold leaf ornamentation, and metallurgical techniques that rival those found thousands of years later. These are the treasures of Sanxingdui, a Bronze Age civilization that was lost to history until its accidental discovery in 1929. The site was formally excavated in the 1980s. It dates back to over 1200 BCE, during the time when the Shang dynasty ruled central China. But what was uncovered in the Sichuan pits bore no resemblance to any Shang artifacts. Instead, it revealed an entirely different civilization, technologically and artistically sophisticated, with a metallurgical understanding that was centuries ahead of its time. At the heart of this mystery are the gigantic bronze masks and statues. Some masks are nearly a meter wide with exaggerated forms, bulging pupils, and stylized ears. The casting required precise control of temperature, mold design, and alloy ratios, with evidence suggesting the use of multi-piece ceramic molds, techniques that wouldn't become widespread in China until much later. The bronze composition itself is remarkable too. Many objects are made with high tin alloys, indicating deliberate selection to create stronger, more lustrous materials. The implications of this are enormous. This means they had access to sophisticated smelting infrastructure, mining operations, and even a centralized economy that was capable of supporting these large-scale artistic and industrial productions. Yet there are no written records. No contemporary Chinese historians mention this place. It appears in no classical texts. This has led some scholars to propose that Sanxingdui belonged to a previously unknown Bronze Age kingdom, possibly linked to the ancient Shu state, mentioned only obliquely in much later writings. The site continued to yield wonders. In 2021, new pits revealed ivory carvings, silk fragments, and even more sealed bronze boxes with organic remains, just hinting at preservation techniques or sacred rituals that are still poorly understood. Researchers are only beginning to map the full extent of the innovations here, but what's clear is this: they mastered large-scale metallurgy and modular design. Control of much of the world was still in the early Iron Age, and Sanxingdui reminds us that civilizations can rise, excel, and vanish without even leaving written records. But their technology, if preserved, can still speak for them thousands of years later. Number 2. The ancient Greek tunnels of Eupalinos, circa 530 BCE. Before GPS, laser leveling, or even magnetic compasses, the ancient Greeks engineered one of the most astonishing feats of civil engineering ever attempted: a tunnel carved through a mountain from both ends simultaneously, meeting in the middle with stunning precision. This was the Tunnel of Eupalinos, a 1,036-meter-long aqueduct bored straight through Mount Castro on the island of Samos in the 6th century BCE. Now, what makes this so astonishing isn't just the scale or the ambition, it's the mathematical genius and surveying technique it required. With no modern instruments, Eupalinos devised a method of excavation that accounted for elevation changes, angle deviations, and geological anomalies over nearly a kilometer of solid limestone. Modern engineers have analyzed the tunnel and concluded that even using today's equipment, that task would be immensely challenging. The construction involved two teams digging from opposite sides of the mountain. When they finally met, they were just 60 centimeters off vertically and a mere meters off horizontally. To compensate, the crews built a small lateral correction chamber to align the final passage. A sophisticated adjustment clearly pre-planned. The tunnel was dug entirely by hand using chisels and hammers in the shape of a rectangle about 1.8 meters high. Inside, a second channel was dug lower down to carry water in clay pipes, while workers could still walk above. No other tunnel from the ancient world, not in Egypt, not in Mesopotamia, not even in Rome, matches this achievement. It remained in use for over 1,000 years, serving as a primary water source into the Byzantine period. The Tunnel of Eupalinos is not just a marvel of engineering, it is the first known example of geometrically calculated tunneling from both ends of a mountain, and its success suggests a level of mathematical sophistication far beyond what most attribute to pre-Hellenistic civilizations. Its survival is a triumph of engineering and intellectual daring. Eupalinos didn't just solve a problem, he calculated a solution beneath 250 meters of rock, and it worked perfectly. Number 1. The Baghdad House of Wisdom and the invention of algebra, the Abbasid Caliphate, the 8th to 9th century CE. In a world where learning was often locked behind monasteries, feudal traditions, or limited to privileged elite, there rose a beacon of intellectual fire in the heart of the medieval Islamic world. A place where astronomy, chemistry, medicine, geometry, philosophy, and poetry were not only studied, but transformed. That place was the Bayt al-Hikmah, the House of Wisdom in Baghdad, established during the golden age of the Abbasid Caliphate in the 8th century CE. And it's one of the most astonishing early inventions that help incubate what was not a physical machine, but a new way of thinking, the invention of algebra. To fully appreciate the impact of this revolution, you have to understand what algebra represented in its time. In antiquity, mathematics was primarily concrete, a tool for trade, land measurement, or basic architecture. Babylonian, Egyptian, and Greek thinkers had made strides in arithmetic and geometry, but they relied on specific numbers and visual proportions. They lacked a general system of abstraction, so what scholars of the House of Wisdom developed was something radically different: a symbolic language for solving problems across all values, not just particular ones. This was algebra, from the Arabic word al-jabir, meaning reunion of broken parts. At the center of this intellectual explosion stood Muhammad bin Musa al-Khwarizmi, a polymath from Khwarazm, now Uzbekistan, whose work in mathematics, astronomy, and geography would ripple across continents. Around 820 CE, he wrote a book, the Compendious Book on Calculation by Completion and Balancing. This was the book that defined algebra as an independent discipline. More than just a mathematical manual, the book was a philosophical declaration. Problems could be generalized, abstracted, and solved procedurally. It wasn't just about what the answer was, it was about how to think about problems that had no immediate numeric solution. Algebra from this era was rhetorical, meaning it was written entirely in prose, not symbols. For example, instead of saying 2x plus 10 equals 30, Al-Khwarizmi would write 2 roots and 10 are equal to 30. This made it accessible to scholars who were not deeply trained in mathematics but fluent in classical Arabic. Yet despite the verbal form, the conceptual depth was extraordinary. His work laid out the solutions to equations involving unknowns, their squares, and constants, and presented practical applications in inherence law, surveying, commerce, and architecture. While modern algebra uses symbols like x and equations peppered with operators, it was the House of Wisdom that planted the seed of abstraction. This opened the door to symbolic reasoning that would eventually blossom into Europe during the Renaissance and Enlightenment. Now, one reason algebra could emerge here and not elsewhere is because the House of Wisdom wasn't limited by the boundaries of a single discipline. It treated mathematics, philosophy, language, astronomy, and theology as part of a unified intellectual pursuit. This interdisciplinary approach gave rise to astonishing leaps, including the use of zero and place value notation adapted from Indian mathematicians, advances in spherical trigonometry to aid Islamic astronomy and prayer direction, the invention of optical theories that predated Newton by 700 years, and refinement of the astrolabe, a complex navigational device that was both scientific and symbolic. The legacy of algebra is incalculable, no pun intended. It enabled the rise of calculus, coordinate geometry, abstract algebra, and even computer science. Yet few people know that it began as a practical toolkit for solving inheritance problems and building irrigation systems in a desert empire. In a time when Europe was fractured by tribal war and the Americas still organized by oral empires, the scholars of Baghdad were solving equations that would define the next millennium. They weren't just ahead of their time, they were building the framework by which time itself would be measured, not by stars, but by your thoughts.